Good day, class. We will discuss Module 2, no? Which is about the environmental systems, including matter, energy, and life. So in this module, you will understand how important it is to view the environment as a system. You are also expected to learn the mechanisms responsible for regulating the system to attain systemic equilibrium. Lastly, you will understand the creation and movement of matter and energy throughout the system through the biotic and abiotic components via biogeochemical cycles to support our planet. Understanding what a system is and how it works will allow us to tackle some of the worst environmental problems that we ever had. So, the environment in its entirety may be regarded as a single system consisting of smaller interconnected subsystems. One way in which a system analysis approach can be useful in understanding the environment is that it draws attention to the ways in which different parts of a system adjust to each other and to external factors. Now, what is the meaning of a system? No, class? So it defines, a network of interdependent components and processes with materials and energy flowing from one component to another. So in other words, class, a system is a group of components that work together to, to perform a function. So now, why do we have to look at our environment as a system? Is human an open system or a closed system? Understanding what a system is and how it works can allow us to tackle some of the worst environmental problems that we've ever had. Systems analysis also emphasizes the importance of understanding the structure of and the relationships between and within different parts of the environment. So, let's have an example. We have here the Aral Sea, It sits in the border of Kazakhstan and Uzbekistan, and it used to be the fourth largest freshwater lake on the planet. The Aral Sea today is a tenth of its original size, at more than 67,000 square kilometers. The Aral Sea was once the fourth largest freshwater lake in the world. Look at now. So in 1950s class, the Soviet Union was irrigating of the Aral Sea to grow cotton and rice. So they undertook a major water diversion project on the arid plains of Kazakhstan, Uzbekistan, and Turkmenistan. The region's two major rivers, fed by snowmelt and precipitation in faraway mountains, were used to transform the desert into farms for cotton and other crops. It wasn't super efficient, It wasn't super efficient irrigation, and so if you compare the pictures, if you watch what happened to the Aral Sea, from until 2019, it essentially became a desert, a desert. And we just see the South Aral Sea on the western margin. The fish all died, and they had an economic collapse. Now, this what happens, no, with the system if we will not manage the inputs and outputs. Now, when we look at the earth, it is a system, no, at the largest level. It's separated from its surroundings, and understanding the inputs and outputs allows us to manage a system. And so the big things that we're looking at are matter and then the energy. So the matter, no, remember, it is what we're made of. And the energy is the ability to do work. Now, if you look at the matter of our planet, it's a closed system? Yes, it is a closed system. Why? Because the amount of matter in our planet is conserved. We don't get new matter from space. So we are stuck with the atoms that we have, and it must be conserved over time. But if we look at the energy, no? However, it's more than an open system. We continue to get energy coming from the sun, and we lose that energy as heat. Okay. We conserve, no? Because the amount in our planet is conserved, no? So, the thing about is that you should understand that it's conserved. And if we are looking at energy, understanding the laws of thermodynamics is essentially important. So, understanding how system work, no, is done through systems analysis. If the system doesn't change, we say that the system is at a steady state or at equilibrium. No? And we can move it towards the steady state using the negative feedback and or away using positive feedback loop. Okay? And so the big picture is that a system is separated from its surroundings, no, using a boundary, and we call this a closed system. Like the matter we have on our planet, no, we don't get new matter. We don't lose matter generally to space. But if we look at the open systems like energy, then there's a flow, no, from the surroundings into the system and vice versa. So, you're a system. Is human an open system or a closed system? So, class, the human body is an open system. Various inputs, no, such as oxygen, food, and water are inputs, whereas waste and carbon dioxide are outputs. And so, big picture, no? A system is separated from its surroundings using a boundary, and we call this a closed system. Like the matter we have on our planet. We don't get new matter. We don't lose matter generally to space. Open systems are those that receive inputs from their surroundings and produce outputs that leave the system. If we look at open system like energy, then there's a flow, no? From the surroundings into the system and vice versa. So positive and negative feedbacks are a fundamental part of ecosystems. Consider the simple system in figure. A pair of rabbits, no, produces several baby rabbits, no? And reproduction can lead to greater and greater numbers of rabbits, no? And this is a positive feedback. If there were an unlimited food supply, the rabbit population would increase indefinitely. But if the growing rabbit population depletes its food supply, starvation will slow or reverse population growth, then it is a negative feedback. So when there are fewer rabbits, the plants recover and the cycle starts again. Disturbances, no? So we have disturbances such as fire, flooding, climate change, invasion of new species, destructive human activities. So, it also interrupts normal feedback loops. Sometimes, systems are resilient so that they return to something like their previous states after a disturbance. Sometimes, disturbances cause a system to shift to a new state so that conditions become permanently altered. So what is resilience and state shift? Resilience is the ability to return to a previous condition from being in a disturbance. State shift, it is an adapt, no, to the condition, not going back to the previous condition, so that conditions become permanently altered. So, ideally, systems tend to be stable over time. If the Chesapeake's nitrogen inputs equal outputs, then the amount of phytoplankton, algae, and other organisms should remain relatively constant. When a system is in stable balance, we say it is in equilibrium. So, equilibrium, it is a relatively stable state that keeps population sizes within a sustainable range. Systems can change, though sometimes suddenly. Often there are thresholds or tipping points where rapid change suddenly occurs if you pass certain limits. Chesapeake base oxygen levels may decrease gradually, without much visible effect until they reach a level at which fish can survive. Then suddenly, decaying bodies of a massive fish kill release toxins and use even more oxygen, which throws the whole system into a downward spiral from which it's difficult to recover. So, we have these emergent properties, no? They arise from the collaborative functioning of a system but do not belong to any one part of that system. Emergent properties are another exciting aspect of systems in which the characteristics of a whole system are more than the sum of its parts. Consider mangroves, no? Consider mangrove forests, which grow along coastlines throughout the tropical world because their direct economic value can be modest. Thousands of kilometers of mangrove-lined coast have been cleared to make room for shrimp, ponds, or beach resorts. However, the mangrove forest provides countless indirect economic values. Prop roots, trap sediment, and stabilize mudflats, improving water clarity and protecting offshore coral reefs from silt. Then mangroves also protect small fish and other marine species. Match commercial ocean fish and shrimp species spend juvenile stages hiding among the mangrove roots. Moreover, the forest protects the shoreline from damaging storms and tsunamis. Collectively, these services can be worth hundreds of times the value of a shrimp farm, but they exist only when the many parts of the system function together. Okay. Now, to understand the systems on our planet, we will deal with matter and energy of our world. So let us first understand what is matter. So matter, no? So before, no? Before we discuss or we understand, no, what is matter, let us first start with what matter is composed of. So matter basically, no, consisting of elements which are substances that cannot be broken down into simpler forms by ordinary chemical reactions. Each of 116 accepted elements has distinct chemical characteristics. So now, atoms are simply the smallest particles that exhibit, no, the characteristics of an element. So this no so I think most of you understand what is the difference between an atom and an element, right? So again, element, it is a element, no, These are the substances that cannot be broken down into simpler forms by ordinary chemical reactions, while atoms are simply the smallest particles that exhibit the characteristics of an element. Okay? So, we have this, matter. Matter, anything that occupies space and has a mass. So, as difficult as it may be to imagine, when you look at a solid object, all matter is composed of tiny, moving particles separated by space and held together by energy. Thus, no, again, we can say that matter is anything that occupies space and has mass. It exists in three distinct and familiar states: solid, liquid, and gas. No? So they are distinct with each other due to the differences in the arrangement of its constitutive particles. We will not dig deeper into its arrangement, but let us focus on its behavior. No? Now, matter behaves according to the principle of conservation of matter. This principle states that matter is neither created nor destroyed. Rather, it can be transformed or recombined, but it does not disappear. Basically, it tells us that everything goes somewhere. In affluent societies, we use natural resources to produce an incredible amount of disposable consumer goods. Everything goes somewhere. Where do the things we dispose of go after the garbage truck leaves? No? As the sheer amount of disposed of stuff increases, we are having greater problems of finding places where to put it. Ultimately, there is no away where we can throw things we don't want anymore. Now, think about this for a second. What are the most atoms present in the human body going to be? Well, let's break it down by percent composition. We are mostly made of water, and so it's mostly going to be oxygen and hydrogen. We are also built out of carbon, but hydrogen is low because it is small in terms of mass. We are also composed of nitrogen, no? Calcium, phosphorus, no? But in general, we are made by the mass of oxygen. Next, if we're going to look at water, no? At water. So it's seawater right here. And what's mostly seawater composed of? We can break it up this way. First, it mostly composed of oxygen. As we like our bodies, no? Since it is mostly made up of water, it's also gonna have sulfur, magnesium, salt, sodium, and chloride. but it's mostly made up of hydrogen and oxygen. So now if we're going to know the mass composition of the Earth's crust. Similarly, it's mostly made up of oxygen, but it is also composed of silicon, aluminum, iron, calcium, sodium, and potassium. So, and now if we look at the atmosphere, it's mostly composed of nitrogen. But we're also gonna have large amounts of oxygen as well, and other trace elements. With that being said, so the oxygen in the atmosphere can eventually become the oxygen in the Earth's crust. Oxygen in water, and it can be the oxygen present in you. This basically shows how matter behaves based on the principle of conservation of matter, no? Because we're not creating new atoms on our planet. It tells us the matter must be recycled over time, or it can be passed and be recombined, but it does not disappear. Now, we are done with matter, no? So, we are done with matter. And the next thing we should do is energy, no? So, energy. What comes into your mind when you read or hear the word energy? Perhaps you are all familiar with potential and kinetic energy, right? So class will first, no? Let us define what is energy. So energy, this is the ability to do work. Diba? Energy was first quantified by James Joule, no? As I said a while ago, it is simply defined as the ability to do work. Energy is often measured in calories, the unit for heat, or it can be in joule, the unit for work. 1 joule is the work done. When 1 kilogram is accelerated at 1 meter per second, 1 calorie is the amount of energy needed to heat 1 gram of your water 1 degree Celsius. A calorie can also be measured as 4.184 joule. Now, energy is classified as either potential or kinetic energy. When we say potential energy, when we say potential energy, it is stored energy available for use. Kinetic energy, on the other hand, is the energy contained in moving objects. I think you're already familiar with this, right? No? Balik-balik na ng potential and kinetic energy. One example of potential energy is the chemical energy. No? Is the chemical energy stored in the food you eat, the gasoline you put in the car. No? It is also an example of potential energy that can be released to do useful work. And then, here are examples of kinetic energy also. First, we have a moving bicycle. The mechanism behind it is that when we start pedaling, we are converting our body's energy into the mechanical form, which is initially the potential energy and ultimately is converted into kinetic energy due to the motion of the wheels. Next, we have a windmill, no? Here, the moving air has kinetic energy that causes the rotation of blades, and therefore, the kinetic energy is then converted into mechanical energy. Lastly, we have a hydropower plant. When the moving water possessing some kinetic energy hits the turbine present in the dam, the kinetic energy of the water gets converted into mechanical energy. So this mechanical energy moves the turbines, no? And then ultimately it leads to the production of electrical energy. Libog? Ah. Okay. Now, when a substance absorbs heat, no? When a substance absorbs heat, the kinetic energy of its molecules increases, or it may be changed state. For example, a solid may become liquid. Similarly, a liquid may become gas. We sense change in heat content as change in temperature unless the substance changes state. So this occurrence can be seen in the environment. For example, heat storage in lakes and ocean is essential to moderating climates and maintaining biological communities. So heat absorbed in changing states is also critical. So as mentioned earlier, we have learned how heat energy behaves. Now, thermodynamics deals with the rates of flow and the transformation of energy from one form or quality to another. So, thermodynamics class is a complex quantitative discipline, but you don't need a great deal of math to understand some of the broad principles that shape our world and our lives. So now we have a car that moves from here to there, no? And it's converting energy. But we are not creating energy. Rather, we are converting it from one form to another. How? Then, where was the energy before it was in the motion of the car? So, it was in the gasoline first. But before that, it was in the crude oil. And even before then, it was in the ancient rainforest until we go back to the energy given off by sunlight. It was then used by the rainforest through photosynthesis. But we were not creating new energy. We can't create new energy. And this shows the first law of thermodynamics, in which energy is conserved, meaning it is neither created nor destroyed under normal conditions. So Earth's energy budget describes the balance between the radiant energy that reaches Earth from the Sun, the energy that flows from Earth back out to the space. Energy from the Sun is mostly in the visible portion of the electromagnetic spectrum. About 30% of the Sun's incoming energy is reflected to space by clouds, atmospheric molecules, tiny suspended particles called aerosols, and the Earth's land, snow, and ice surfaces. So the Earth system also emits thermal radiant energy to space, mainly in the infrared part of the electromagnetic spectrum. So the intensity of the thermal emission from a surface depends upon its temperature. Now, the Earth atmosphere system is constantly trying to maintain a balance between the energy that reaches Earth from the Sun and the energy that flows from Earth back out to space. If the Earth system is changed either through natural phenomena, such as volcanoes or man's activities, and an imbalance in the Earth's energy budget occurs, the Earth's temperature will eventually increase or decrease in order to restore an energy balance. So now, second law of thermodynamics states that when energy is used, it is degraded to lower quality forms, or it dissipates and is lost. When you drive a car, for example, the chemical energy of the gas is degraded to kinetic energy and heat, which dissipates eventually to space. So, the second law deals more with the systems because we're gonna have inputs into the system of the car and then we're gonna have outputs. So now, if we look at the amount of energy that goes into the car, we can think of the energy of the gasoline itself. We're using some of the energy for the kinetic motion of the car, but we are also losing some of the energy in friction, heat, and in sound. And so, what the second law of thermodynamics talks to is, again, second law of thermodynamics talks to is that at each interaction, at each interaction, at each point along the pathway, we are losing some of the useful energy that is becoming heat, which is not usable on our planet. So remember, the second law of thermodynamics, the second law of thermodynamics talks, that at each interaction, at each point along the pathway, we are losing some of that useful energy and it's becoming heat which is non-usable on our planet. So now, how does the second law of thermodynamics apply to organisms and biological systems? So organisms are highly organized, both structurally and metabolically. Constant care and maintenance are required to keep up this organization, and a continual supply of energy is required to maintain these processes. For instance, every time a cell uses some energy to do work, some of that energy is dissipated or lost as heat, no? If cellular energy supplies are interrupted or depleted, the result, sooner or later, is what? Is death. Okay?